Hello, good people. Welcome to video number two. Video number two, we're still practicing this integral test. Remember, integral test has three conditions. Number one is if I can create a function, parallel function, is the function positive? We're going to ask ourselves that. Is it continuous? And is it decreasing? If those three things are satisfied, then I can use the integral test. If my integral is easy to integrate, my function is easy to integrate. So first of all, I got to find a parallel function. So f of x is equal to, now think of it, if n is my variable, then I'm just going to replace those with x, and this is going to be my parallel function here that I'm going to use. But I need to check, is it all these three things? So I go to my calculator, and I go over here, and let me go to the denominator. Let's delete that. And we're going to do x natural log of x. So I'm going to graph this to see what happens. Is it decreasing? Is it continuous? And is it positive? So I notice that there's a discontinuity, right? But let me go back and check. Oh, I'm starting at 2 to infinity. So when I look at my calculator, if I start at 2, that's right here, to infinity, oh yeah, there are no problems in terms of continuity. It's continuous. It's above the x-axis, so it's positive, and it's getting smaller and smaller and closer to 0, so it's decreasing. All three things, all three conditions are satisfied. Check, check, and check. Great. So now we're going to take the integral from 2 to infinity of this function, which really means I need to take the limit as b approaches infinity of this improper integral. So I'm going to say from 2 to b of this. Now, as I start to work this out, how do I find the antiderivative? If you want to pause and think about it, what would be the way to start, feel free to do so. And I'll give you 3 seconds to pause, and then I'm going to come back and I'm going to show you the way to get it, the antiderivative. It turns out this integral is actually a u substitution. It's a u substitution where u is natural log of x. So if I come over here, u is a natural log of x. That means du is 1 over x dx. Well, hey, look, I have 1 over x dx. Perfect. So that means I can rewrite this as the limit as b approaches infinity of, and you know what I'm going to do? I'm going to go ahead and switch the limits of integration here, and I'm going to say I'm going to substitute 2 into the formula. That'll be natural log of 2 on the bottom. B into the formula. This is going to be the natural log of b on the top limit. And I'm going to rewrite this as 1 over u, because this became u. And then this part I'm going to replace with du. Oh, well, the antiderivative of 1 over u is natural log. So really, I'm going to take the limit as b approaches infinity of the antiderivative is the natural log of the absolute value of u, evaluated from this bottom limit to the top limit. Now, this is kind of weird because I'm taking the natural log of something, and the values I'm going to substitute in are natural logs. So it's going to look funny, but I'm going to do it anyway. The natural log of the absolute value of the natural log of b minus the natural log of the absolute value of the natural log of 2. By the way, I don't necessarily need the absolute values because I know my b's are always positive. So this is always going to be positive. And the same thing here. I know 2 is positive, so this is always going to be positive. I don't really need the absolute values, but I'll leave them in there anyway. As I plug in big values into natural log does increase without bound, does go to infinity. And if I take the natural log of the natural log, that means I'm taking the natural log of big values. Well, that's also going to go to infinity. So this first part goes to infinity. And it really doesn't matter what's over here, because if the first part goes to infinity, then this thing diverges. I don't know why my pen is dragging here. Natural log of the natural log of 2. So my whole thing is going to diverge. But therefore, that means that my original series will diverge by the integral test. Remember, so this thing diverges because this thing diverged. So build a function that's a parallel function to the nth term formula here. Figure out if it's positive, continuous, and decreasing. If it is, can you take the antiderivative? Can you integrate it? If you can, then take the antiderivative, substitute the top value, substitute the bottom value. Since we're going to infinity, it's going to involve an improper integral. We are mixing a lot of ideas in this problem, right? We're mixing the idea of use substitution with the idea of an improper integral. Whenever we have an infinity, I have to use a limit, with the idea that the integral value, convergence and divergence of the integral value, corresponds to the infinite series that we are studying in this unit. That's a lot, but you can do it. It's not that bad. As a matter of fact, we're going to do the next one, not the next one on your paper, but we're actually going to do number 3. So this is going to go back to something that some of you watched and some of you didn't because it was optional. Can I find whether or not this series that looks like this converges or diverges? So what's the pattern here? Well, I notice that all of these are fractions, including this, because this is really 1 over 1, right? So if it's 1 over 1, 1 over 1, 1 over 2, 1 over 3, 1 over 4 that I'm adding, then really I'm adding this pattern of 1 over n, where n is the index down here that I'm plugging in, 1, 2, 3, 4, and that's how I'm building my terms. Hey, this is the harmonic series we talked about. The harmonic series from the last video, or I guess it was the nth term test? The nth term test video, yeah. So now we're going to be able to prove whether or not this converges or diverges. How? By building a definite integral, an integral that goes from 1 to infinity, of the parallel function, which is 1 over x dx. Well, that means I have to take the limit because I'm involving infinity. So this is an improper integral. I have to do this. Can I take the antiderivative? Heck yeah. Look, this is just a natural log of x. And I'm going to evaluate that from 1 to b while taking the limit as b approaches infinity. So go ahead and plug in the top. I think I didn't put the line here. Plug in the top and plug in the bottom. So the limit as b approaches infinity of the natural log of b. And again, I don't need to put the absolute values because b is going to be positive because I'm moving to the right, minus the natural log of 1. What's the natural log of 1? Well, the natural log of 1 is 0, so that goes away. What happens to the natural log of b as b goes to infinity? Oh, this is going to go to infinity. So this integral diverges. And if the integral diverges, that means the original series also diverges by the integral test. This series has its own name. It's the harmonic series. And harmonic series are always divergent, and I can prove that by using the integral test. This is one of those that you need to remember because it's going to come back to help us when we do the comparison tests next week. So what's the big idea? The big idea is if I can create a parallel function and take the integral of that function from my starting point to infinity by doing an improper integral, if I can take the antiderivative and do all that business, whatever the answer is there, let me rephrase that, whatever the outcome is there, does it converge because there's an answer? Does it diverge because there's not an answer? Then that's what's going to happen to the original series. If it does converge to a number, that doesn't necessarily mean that the series converges to the same number. Actually, it doesn't. It's different, but at least I know that it converges, and that's the important part. Welcome back in the third video. We'll do some more examples, and then we'll wrap it up.